Welcome back to the deep dive. I'm excited for today's topic, even if it sounds a bit scary at first. We're diving into the world of linear equations and figuring out how to solve systems of these things. And then there's this whole matrix inversion mystery that we're going to try and unlock.
Sounds complicated.
It can be, but that's why we're here. We're going to break it down, look at the research, and see just how important these techniques are in scientific computing. Like, how do the experts handle those massive calculations and do it both quickly and accurately?
Right, because you can't have a rocket going to the moon based on bad math.
Exactly. And there are different ways to work with matrices, but we're going to keep our focus on the core techniques that get the job done.
Because in the end, that's what matters.
Absolutely. So let's jump in and start mastering those matrices.
All right, let's do it. It's pretty amazing when you think about it, but behind all these complex scientific and engineering things we have, it's the language of matrices that's doing a lot of the heavy lifting. When you've got tons of equations and a bunch of unknowns, finding that one set of values that makes everything work can seem like an impossible puzzle.
A lot of moving parts, yeah.
Yeah, and matrices help us organize the chaos. Like you got this standard form, xx equals b doll. Xx is like a container holding all the coefficients from the equations. Six represents all the unknown variables, and dollars has the constants from each equation. It's pretty elegant when you see how it all fits together.
Okay, so if our matrix dollars is well behaved, meaning it has an inverse, then we can just find $6 using the formula xx equals a1b, right? That seems simple enough.
Yeah, it's the classic textbook solution, but there's a catch.
There's always a catch.
Right. Actually calculating A11 and using it directly to solve for $6 can be tricky. It's kind of like imagine trying to thread a needle during a hurricane. Tiny errors in the calculations, those rounding errors that happen in computers, can get blown way out of proportion
And throw everything off.
exactly, leading to a solution that's, well, just plain wrong. And that's what we call numerical instability. It's a real headache.
So if finding the inverse is risky, how do we reliably solve for $6 in that a bed equation?
We use a much more stable and elegant method. It's called LUP decomposition. The cool thing is, any non-singular matrix, which is basically a matrix that has an inverse, can be broken down into three special matrices. We call them PA dollars and $2. So it looks like this. PA equals LU1. PA dollars is a permutation matrix. It keeps track of any row swaps we have to make. Dollars is a unit lower triangular matrix, which means it's got a bunch of numbers below the main diagonal and all ones on the diagonal itself. And $2 is an upper triangular matrix, so it has numbers above the main diagonal.
Okay, so we've got our original matrix transformed into this combination of few dollars and $2. How does that help us find the solution to xx equals b doll?
It's actually pretty clever. We start by rewriting our system as PXX, and because we know PA is the same as BBOU, we get x equals PB doll. Now, let's introduce a temporary variable, PLC. This makes our equation a bit simpler. LIOU equals a BB. Now, here's where the triangular matrices come in handy. Since Flower is lower triangular, we can solve for each component of Euler one at a time, starting from the top equation and moving down.
Kind of like a step-by-step process.
Exactly. And we call this forward substitution. Once we have Eulers, we can plug it to hum dollars and solve for 6s. Since C dollars is up a triangular, we start from the last equation and work our way up. This is back substitution.
So instead of that one potentially unstable matrix inversion, we have two much simpler systems to solve.
And the substitutions are really efficient, right?
Right, they are.
Each of them only takes about 22 steps for a null times null system. And the entire process of solving xx equals b bucks using LUP decomposition, which we call LUP SLVE, is also really fast. It's way faster and more stable than trying to invert the matrix directly.
Now, you mentioned LU decomposition earlier without the P. How is that different? When can we just use LU?
Yeah, good question. LU decomposition is a bit simpler. We just factor LU dollars into LU directly without that permutation matrix. There are a lot of matrices that can be factored this way. And the process of doing this is very similar to something you might have learned in algebra class, Gaussian elimination.
Where you eliminate variables one by one, right?
That's the one. And in this world of matrices, something called the Schur complement pops up. It's basically what's left of the matrix after you've eliminated some variables. The numbers we divide up by during this elimination process are called pivots. Now, this LU decomposition algorithm is pretty efficient too. It takes about 393 steps to do the factorization. And the best part is that we can store a little m and $2 in the same memory space as the original matrix. Now,
So LU seems simpler. Why do we need LUP with that extra permutation matrix?
it goes back to that numerical instability issue. Sometimes during LU decomposition, we might have to divide by a pivot that's either 0 or very close to 0. And dividing by a really tiny number can cause those tiny rounding errors to explode.
And mess everything up.
Totally. LUP decomposition solves this problem by using a technique called pivoting.
Pivoting, huh? Like rearranging things.
You got it. In each step of the decomposition, we look at the current column and find the entry with the largest absolute value. Then we swap the current row with the row that has this largest value. This makes sure that our pivot is as big as possible, so we don't end up dividing by tiny numbers. And the permutation matrix keeps track of all the row swaps we do.
Ah, so Pyolars is like a careful record keeper.
Exactly. And just like LU decomposition, LUP decomposition takes about 303 steps.
Okay, so LUP is like the reliable workhorse for solving linear systems. Now, let's talk about actually finding the inverse of a matrix, that A1 we were talking about earlier. You mentioned LUP is usually better for solving XX equals BZO, but sometimes we need the inverse directly. Why is that?
You're right. While solving systems is the main goal, there are times when you need to have the inverse explicitly. It's helpful in some theoretical situations and some specific applications. And what's really neat is that we can use LUP decomposition to calculate this inverse.
So we can use what we already know.
Yeah, exactly. It's all connected. You can think of finding the inverse as solving a bunch of linear systems at once. Each column of LDO can be found by solving a system like ACD equals A, where the $6 is the ith column of the inverse, and the able is a special vector with a 1 in the ith position and zeros everywhere else. So we can use LUP solve EE to find each column of the inverse. And since LUP solve EE takes $2 steps, and we need to do it for each of the not columns, the total time to find ADA is also 3 and 3, 3. The same as the time to do the LUP decomposition.
Wow, it's amazing how everything fits together. The material also talks about the connection between how hard it is to multiply matrices and how hard it is to invert them.
Absolutely. In theory, matrix multiplication and matrix inversion are basically equally difficult when you look at how the time it takes to do them grows as the matrices get bigger. There's this cool theorem, Theorem 28.1, that says if you have a way to invert an $1 times null matrix in some time, let's call it 1 in n, then you can use that same method to multiply two $1 times matrices in roughly the same amount of time, like $1. The proof uses a clever trick with a larger matrix that's made up of blocks. It's pretty neat.
So if we find a faster way to do one, it speeds up the other.
Exactly. And the other way around, too. That's Theorem 28.2. If you can multiply two 1 times matrices in a dollar time, then you can invert any non-singular times a matrix in about dollar time. The proof for this one is a bit more involved, but it starts by looking at a special type of matrix called a symmetric positive definite matrix.
Symmetric positive definite. What's that?
It's a mouthful, right? A symmetric positive definite matrix is a matrix that's equal to its own transpose, which means it's symmetric along the diagonal. And if you take any non-zero vector and multiply it by the matrix and its transpose, you always get a positive number. There's some really nice properties.
So how do these special matrices help us with the general problem of inverting matrices?
The proof uses this divide and conquer approach to invert these special symmetric positive definite matrices, again using the Schur complement. It shows that the time to invert one of these matrices is basically the same as the time to multiply matrices. Then, to extend this to any non-singular matrix, the proof uses this neat trick. 1 love 1, 8 needs 1 AT. It turns out that if 1 all is non-singular, then AT key is always symmetric positive definite. And this whole process takes about the same time as matrix multiplication. They even deal with cases where the dimension of the matrix isn't a power of 2 by basically putting the matrix inside a larger one. The text also mentions using LU decomposition of ATE2 to solve 8T, but it points out that LUP decomposition is still better in practice.
Okay, so we've gone deep into these connections between different ideas in linear algebra. The last part of the chapter we're looking at digs even deeper into these symmetric positive definite matrices and how they're used in least squares approximation.
Right. Those matrices pop up everywhere. And they have some really important properties. Like there's lemma 28.3, which says that any positive definite matrix always has an inverse. And lemma 28.4 tells us that if a matrix is symmetric positive definite, then any square block you take from the top left corner of that matrix is also symmetric positive definite.
Like little mini versions of the big matrix.
Exactly. And remember that Schur complement we talked about before. Well, lemma 28.5, the Schur complement lemma, tells us that the Schur complement of a symmetric positive definite matrix is also symmetric positive definite.
So all these special properties, what do they mean in practice?
One really useful consequence is what corollary 28.6 tells us. When you do a standard LU decomposition on a symmetric positive definite matrix, you never run into that dividing by zero problem, and all the pivots you get are positive. This means it's a very stable process. Although, as we said before, LUP decomposition is often used in software just to be extra safe.
Okay, so these symmetric positive definite matrices have some really nice theoretical and practical advantages. But how do they connect to this least squares approximation idea?
So least squares approximation is what we use when we have more equations than unknowns.
Mm-hmm.
Like when you're trying to fit a model to some data. In these situations, there's usually no exact solution that satisfies all the equations perfectly. So what we do is try to find the solution that gets as close as possible, minimizing the errors.
So it's all about finding the best fit for the data.
Right. And one way to measure the error is to take the differences between what our model predicts and the actual data, square those differences, and add them all up. This usually leads to a system of equations that we can write as axi equals y is y, where axi represents the unknowns we're trying to find.
And we're trying to find the values of Tabor dollars that make the model fit the data best.
Exactly. The solution that minimizes that sum of squared errors comes from solving what's called the normal equation, ATACE equals ATAYY. And if our matrix doubler has full column rank, meaning its columns are all independent, then this matrix ATAT is guaranteed to be symmetric positive definite and therefore non-singular. This means the normal equation has a unique solution, given by ATA doubles 1 ATOR, and that ATA1 is called the pseudo-inverse of AT-arrow, often written as a plus dollar.
Did the material give us any real-world examples of how this works?
It does, actually. One example shows how you can fit a quadratic polynomial to 5 data points using this least squares method. And another example uses it to fit a more complex curve to data about the amount of carbon dioxide in the atmosphere. In practice, to solve this normal equation, you'd usually start by calculating ATY walls and then find the LU or LUP decomposition of ATAI to efficiently solve for 2-mount.
This has been an incredible deep dive. We've covered so much ground, from that basic SX beta vol problem to the power of LUP decomposition and how it helps us invert matrices. We even talked about how multiplying and inverting matrices are related and how these special symmetric positive definite matrices are used in least squares approximation. It's clear that these methods are crucial for scientific computing.
I agree. It's amazing how much we rely on these techniques.
Yeah.
We saw how LUP decomposition is a really efficient and reliable way to solve linear systems, taking about 2 and 2 steps after we do the decomposition, which takes about 3 steps. Matrix inversion also takes about 3 steps. These algorithms are the workhorses behind so many things we do in science, engineering, and technology.
Yeah, we don't always realize it, but these methods are everywhere. So as we wrap things up, I want to leave you with something to think about. We've seen how these matrix methods can be used to solve complex problems and find the best solutions, even when there's no perfect answer. Where else do you think these tools might be used, maybe in places you wouldn't expect? It's fascinating to think about how these seemingly abstract mathematical ideas have such a huge impact on our world. Thanks for joining us on the Deep Dive.
Thanks for having me.